We now review recent content on conditional probability, unconditional probability, and Bayes' theorem. To start with, recall the setting that we've looked at in earlier recordings. You have some event A, and you have some conditionals on it, such as B given A or B given A bar. Unconditional probability was where we were able to strip out the conditions. In this case, we're able to remove the A and A bar and find the probability of B alone. Bayes' theorem was used in the situation where you need to reverse the order. In this case, we started with B given A, and we reverse it to get A given B. Sometimes the information you're given doesn't quite fit what you need. Notice that in all of these formulas, we had the probability of B given either A or A bar. If your question gave you the complements, you can flip it around. For example, if I know the probability that B did not happen, given A, then the probability that B did happen is 1 minus that. For example, if there is a 90% chance that I do not fail the test after studying all night, then there is a 10% chance that I do fail the test after studying all night. Hopefully, that won't happen. Likewise, if the conditional was given in the reverse of what we wanted, well, we can't actually fix that. What we can do, again, is flip the event that you're looking at. So looking at that studying example, if A was that I study a lot, then A bar would be that I don't study a lot. When I know information about outcomes when I don't study, I can't find information about outcomes when I do study. But I can flip around my B and B bar. So let's turn to an example, and as we work through this example, we'll look at our formulas and try to figure out what applies in each setting. So Brett and Margot have each thought about murdering their rich Uncle Basil in the hopes of claiming their inheritance a bit early. Not very good nieces and nephews. Brett puts rat poison in Uncle Basil's cake. Margot puts cyanide in his chocolate mousse. The probability of rat poison being fatal is 60%, while cyanide has a 90% chance. There is also a 60% chance that Uncle Basil will have the chocolate mousse tonight, otherwise he eats cake. So this is a bit morbid, but let's look now at the probability that Uncle Basil dies of rat poisoning. So the first step in any problem involving probabilities is write down the probabilities. So my event here, well, I could look at this as cake or chocolate mousse, but what really is fatal is the poison, not the cake. So I'm going to put R as the event that he consumes rat poison and C as the event that he consumes cyanide. However, there's really only two things here, an event and its complement. So instead of making a new event for cyanide, that's just the complement of the rat poison case. Moving on to probabilities, we were told that there is a 60% chance that he eats chocolate mousse. Usually we write things down in the order in which the variables appear, but this emphasizes that you need to actually look at the substance in the question. Chocolate mousse, let's see, that had cyanide in it. So it's 60% chance that he does not have rat poison. And the remaining 40% would be the probability that the uncle eats rat poison. What about conditionals? The probability of dying if you have rat poison is given as 60%. The probability of dying with cyanide is given as 90%. Now we move on to the question. What is the probability that Uncle Basil dies of rat poisoning? So what does that mean? That's the probability of death and rat poison. This is not a conditional probability. We were told that the probability of death if he consumes rat poison is 60%. But we no longer want the if situation. We're going into the evening, we say, don't know what's going to happen tonight. What's the chance that Uncle Basil, sometime overnight, has died of rat poisoning? Maybe he eats the chocolate mousse. That won't happen then. So there are two ways this can be broken down with conditional probabilities. Recall that the probability of an intersection is found by taking one variable conditioned on the other. So we might want the probability he dies conditioned on consuming rat poison, or the probability he has rat poison conditioned on having died. So both formulas at the bottom here are perfectly valid. At this point, we need to look at our data and see which of these makes sense to work with. Well, in the data, we were given the probability of death given rat poison. We were not given the probability of rat poison given death. So we'll use the top one. Plug in the numbers that you were given, and we find there is a 24% chance that Uncle Basil will die of rat poisoning tonight. Recall, this is not the 60% figure in the data because Uncle Basil might not even have the rat poison dessert tonight. He might have chocolate mousse, in which case there is a 0% chance of death by rat poisoning. Now let's look at a second problem from this. What is the probability that Uncle Basil dies tonight? This is what we're probably actually interested in. Are Brett and Margot going to get their inheritance? Big question. Let's see what happens. Well, first we write down what is the probability we're trying to find. We're trying to find the probability of death. Notice there is no condition anymore. So this is unconditional, in contrast to the data given in the question where we had conditions. So again, unconditionals are where you strip out the conditions given in the problem. Look at the formula at the top of the screen. Plug that in with death and rat poison. Put the numbers in, and we find there is a 78% chance that Uncle Basil is going to die tonight. So a 24% chance that he is going to die of rat poisoning tonight, but overall a 78% chance that he is going to die. So this is not going to be a good night for Uncle Basil. Finally, let's look at our last problem here. If Uncle Basil dies, what is the probability that Brett's poison is responsible for his death? So was Brett the killer, or was it Margot? To answer this question, we break it up into parts. First, we have our condition. Uncle Basil dies. Then, we have the probability we're trying to find. Is the poison responsible? So death is our condition, and rat poison is the thing that we want to find out. Looking at our data, we had those variables reversed. We were given the probability of death given that he consumed rat poison. Now we want rat poison given that he died. That reversal is the situation for Bayes' theorem. Plug in that complex formula for Bayes' theorem, and I would point out students make a lot of mistakes in writing down this formula. Please be very careful when doing it. I'll find, for example, on the first line here, somebody might correctly put D given R, but they multiply it by P of D. Sometimes the variables get reversed. There's a lot of things that can happen. Always be careful with these formulas. They're very easy to get wrong. Substitute in the information we have about the mortality rate of rat poison and cyanide and the likelihood that Uncle Basil has chocolate mousse or cake, and we find a 31% chance that Brett is responsible for Uncle Basil's death. So what does that mean? Well, that means that there is a 69% chance that Margot is responsible. Obviously, the police should go and look in more detail, maybe check poor Uncle Basil's stomach and see what's in there. But if we were to venture a guess, Margot is probably the killer.